So this is all about ultraviolet and visible spectroscopy, short form UV-Vis, okay? And this is the only video on this spectroscopy. All right, so first of all, just a little bit introduction on this one is that UV-Vis spectroscopy is a very different kind of spectroscopy, okay? There is really not much you can do with spectroscopy with this one. Because it doesn't give you the structure of anything. The only thing you can figure out from UV-Vis is the degree of conjugation, okay? So conjugation meaning alternate double bond, single bond, all of that. So what kind of conjugation you have is the only thing. So not also like how many double bonds. I mean, you can eventually calculate that, but otherwise there's really not a whole lot you can do, okay, with UV-Vis. So first of all, we do both UV and visible together, okay, in UV-Vis spectroscopy. And in both cases, what is happening is that the electrons are getting excited and electrons are moving from one energy level to another, okay. Now remember, we compare with other spectroscopic techniques also, okay. And so in IR, it was a little bit different, right? IR was all about molecular vibrations. Here, it is actually about electron transitions that are occurring. You can use just one instrument for UV and visible spectroscopy. Actually, sometimes you can also use IR, depends on the energy source. But generally, UV-Vis is done together. The units for this one are going to be in nanometers, okay? So it's different. It's different. Okay, and don't forget about the relationships of energy and frequency and wavelength and all of that. Okay, we'll talk about that too. Okay, so here is a first look at a spectrum, what it looks like. So this one is, normal kind of a thing where you have hills and mountains and whatnot. In this case, there's only one, okay? But depending on what kind of compound you have, you can have more peaks also in there, okay? So here you have two axes, of course, as usual. So here the x-axis is going to be nanometers. This is the wavelength, lambda. You can see that. And the y-axis is absorbance. Now, the absorbance, you have to really take care of this one, okay? And I'm going to talk about that when we make the sample. We'll talk about, sample preparation, but otherwise you have to be careful, okay, about this absorbance, because sometimes your spectra can go out of scale, okay? So we'll talk about that, all right? But anyhow, and then of course you have this lambda max, which is the height of, which is the peak here that you get. The tallest peak, at which wavelength do you get that? That is called lambda max, okay? That's the maximum wavelength. You can have more than one lambda max. This one only has one, okay? So it depends on, what you're studying. Okay, so let's talk about why we are actually seeing any kind of spectra here, all right? So remember that we are talking about electron transition. So when you're talking about an electron transition, well, you have electrons, we know that, everybody has electrons, fine. But if you give them energy, there are two things you can do. Either you can move them to a higher location or you can completely eject them out. So if you move them to a higher location, well, you need to have a location. If you're ejecting them out, you're making a cation. That's not a spectroscopy, okay? So that's a different thing. So keep that in mind, okay? That when you have an electron transition, that electron transition means that electron is going to come back to its original state eventually, okay? So you're not getting rid of the electron, you're just moving it from a lower energy level to a higher energy level. So how do we get these levels, okay? And that is explained by the molecular theory. The molecular orbital theory. So molecular orbital theory says that if you have any number of atomic orbitals and you combine those atomic orbitals to form molecular orbitals, you get the same number of molecular orbitals. So two atomic orbitals give you two molecular orbitals. Now, you have different kinds of orbitals, right? When you form molecular orbitals, remember you have sigma bonds and pi bonds in any kind of a compound, or you may have all sigma bonds, you may not have any pi bonds, okay? But the thing is, you have all of these. So molecular orbital theory is really very systematic way of placing electrons in these different kinds of molecular orbitals. Okay, so we're not going to go into the molecular orbital theory in depth, but I just want you to get an idea of how we do this. Okay, so any compound, and again, you know, they're going to be sigma bonds and pi bonds. I'm not going to cover all of them, but here is what happens is that when you have any kind of orbitals, and let me write it here for you. So if you combine an orbital, atomic orbital, atomic orbital, here is an electron, here is an electron. So when you combine these two, you end up getting two molecular orbitals. So one here, one here. This is high energy, and this one is low energy. Where do you find the electrons? You find them low energy. Okay, so that's kind of what happens with the molecular orbitals. Now, depending on how many atomic orbitals you're combining, you can have many of these. Okay, generally sigma bonds are going to be way low, okay, over here, and the higher energy one is going to be way high. That's for the sigma bonds. Okay, the pi bonds will fall in the middle. And then, you know, there is a certain point you start with for the energy and certain point where you finish, because if you provide more energy, remember, electron can eject out, and that's not the point. Okay, so you have a certain amount of energy levels you're looking at over here. So you can have, depending on, as I said, how many atomic orbitals you have, you can have many here, 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 and then the same thing you will have on the top, okay, with the high energy. And let me show you what I mean by that is when you start having molecular orbitals, it's almost like a mirror image. Okay, so for example, if you have 4 molecular orbitals like this, then you would also have 4 molecular orbitals like this, which are high in energy. The ones that are high in energy are called anti-bonding. I mean, it's just written over here, right? I have to explain it to you. And the ones at the bottom, these are called bonding MOs. So anti-bonding MOs and then bonding MOs. Anti-bonding MOs are all given by stars. So you know that this is anti-bonding. Where are the electrons? Electrons are usually going to be in the bonding MO. Why? Because they're low energy, so they like to stay there. Okay, so what happens in UV spectroscopy is that you have an electron transition going on when you provide energy to a molecule. So what happens? What happens, I mean, I'm changing my color here, not my color, pen color. This is what happens. These electrons, which are in the highest occupied molecular orbital, HOMO, will jump to the lowest unoccupied molecular orbital, which is the LUMO. So electrons are jumping from here to here. That's what's going on. That is the electron transition that's going on. Okay, how much energy do you need? Well, how much energy you need depends on how far they are. How far they are depends on how many pi bonds there are, because remember, sigma bonds are on the top and the bottom. Okay, so which means in the middle you're really going to have only pi bonds that will cause this kind of a transition, because pi bonds are lower in energy. I should say higher in energy, not lower. I was going to say like they're more reactive, right? So they're higher in energy. And so the HOMOs and especially the HOMOs that you're going to find, the highest occupied, will be pretty much all the pi bonds. Okay, so you will have this electron transition going on from the HOMO of a pi bond to the LUMO, which is also the anti-bonding. Because remember, right here is the node, and in the node, the opposite side, the anti-bonding, is completely the mirror image, okay, of the bonding side. So hopefully I've explained to you a little bit about how these orbitals exist, okay? And this whole point of how you make this and how you write these out, this is a complex process, okay? It can be simple also. It can be simple depending on what kind of molecule you're working with. So you fill out these energy levels, you fill out all of these, and then you can then determine the distance between the HOMO and the LUMO, and also how many you're going to have here, right? our job is not going to be to write out all of these atomic orbitals or bonding orbitals, excuse me, okay? So don't get scared by that. I was just trying to explain to you how these things are working. So now when you see something like this, you know what I'm talking about. That's all. Okay, so this is the anti-bonding, this is the bonding pi. See the pi here and see the anti-bonding pi. This is the LUMO, which is the unoccupied. This is the HOMO. Now I really have not gone into the depth, okay, about explaining to you about these anti-bonding. See these wave functions here, the wave functions here in opposite spins here, so plus and minus. Remember, they create a node, and that's the higher energy configuration possible. Okay, so generally you would want to have something that overlaps. So here the positive of the wave function will overlap with the positive. Okay, that is a a better overlap than this one. So this is low energy, this is high energy. So what is happening? The electrons are going from HOMO to the LUMO. The energy required here is 686 kilojoules, for example. Okay, let's look at something more. So hopefully things will become better for you. Okay, so here is now for butadiene. Butadiene has 2 double bonds in there. Okay, so in the case of butadiene, you have more electrons in the pi orbitals, and look at that. This is the anti-bonding, and they have no electrons in them. So now here, these two have gotten a little bit closer because now you have more bonds in there. So these two have gotten closer. So it needs a little bit less energy. Okay, I wrote that over here. So in alkene, just a plain alkene ethene, it was 686, but here look, you only need 540 kilojoules. Okay, why? Because they are closer in energy. But what is important for us, as much as energy is also this wavelength. Okay, that is also important to us because that is what we are looking at. Okay, we can also always calculate how much energy is going to be required. That's not a problem. Okay, but as far as our technique is concerned, for UV-Vis, we are looking at nanometers. Okay, so that's really what our energy translation will come out to be, is that how much of wavelength we are going to see. But anyway, this is the transition that's going on. Let's look at some more over here so you can see a comparison, okay, of how this is working. So if you have 2 double bonds, 3 double bonds, and then 4 double bonds, and then this is your limit for the lower and the higher, okay, bonding and the anti-bonding bonds over here. So the energy gets lower and lower and lower. Why? Because the HOMO and the LUMO are getting closer and closer. Why are they getting closer? Is because the number of pi bonds have increased, so you need to have a placement for those molecular orbitals. Okay, and so that is how the HOMO and LUMO conjugation and energy transition is working for us. Okay, so I hope you understand what I'm trying to tell you. So what we are looking at is that the more conjugation you have, the less energy it takes for electrons to transition from one to the other. Now remember, energy and wavelength, opposites. Okay, inverse relationship between them. So this is the theory really, okay, for all of the UV-Vis, is these electron transitions from HOMO to LUMO. Okay, so here is the wavelength given to you for all of these. So if you have butadiene, that will absorb at 217 and then gets higher and higher. Okay, and again, this is because of conjugation. Why conjugation again? Because you have more double bonds in there. So the conjugation part is also an important thing. We'll, you can have many double bonds also in there, and you will still get more transitions possible. Okay, so not everything has to be conjugated, but conjugation does help, okay, in there. So the more the conjugation, the more the double bonds, then the less energy is required, okay, in there. Wavelength, higher wavelength means less energy. Smaller wavelength, higher energy. This is more towards the ultraviolet. This is more towards the visible region. Okay, Let's look at the instrumentation for UV-Vis. It's very similar to IR, some differences here, okay? But otherwise, you do need an energy source. Now, this is going to be within the UV-Vis region. You need to have the sample. Here, you also need a reference, okay? So, reference would be because you need to dissolve your sample in something, okay? And I'm going to talk about that in the sample preparation. But because you're dissolving your sample in a solvent, you need to make sure that you nullify that solvent, okay, in there. So that's why you need to have a reference cell for that, okay? Then both of them come through here to the detector. Then the solvent is subtracted. Once that is subtracted, you end up getting your spectrum, okay? That's it. So then you have an output. So again, energy source, sample, detector, output. So the sample preparation is very simple for UV-Vis. Okay, you need to have a you need to dissolve the sample in some solvent. Now, generally for organic compounds, that would be dichloromethane or methanol, chloroform, something like that. The main thing is that they should not absorb in the visible region. You also need a sample holder. The sample holder is a cuvette. Now, depending on whether you're doing UV spectroscopy or visible, or if it is UV-Vis, you want to make sure that the glass also does not absorb, okay, in the UV-Vis region. So, you know, you have to kind of watch out for these things when you're preparing your sample, okay? So there's different kinds of cuvettes that you can get, which are completely invisible or they're inactive in UV-Vis, okay? That's the quartz kind. But anyhow, that's something you have to, you know, make sure of. Then your again, as I said, your solvent also should not absorb in the UV-Vis region. So you can get spectral grade solvent, not a problem. So here's a cuvette. So you take your solvent and then you make it in the right concentration, okay, with your sample. Now, what I meant by the right concentration, okay, and you remember I mentioned this to you before, is how your sample, if it's too concentrated, then, you know, it can go out of scale. So said here is the absorbance, here is the wavelength, okay? So if it is too dilute, maybe you don't see something, okay, in there. So let's say this is going from 0 to 10. Generally, that's the scale, okay? And then sometimes if it is too concentrated, then you don't see the lambda max. Okay, and that's the whole point of UV-Vis. So if you don't see the lambda max, then you have to dilute your sample down. Once you dilute it down, then you can see the lambda max. So which means we're playing a little bit like Goldilocks here, you know, get the right amount of concentration. And since if you're just running your sample just for testing sake, then you don't really have to calculate the concentration, okay? Although in UV-Vis you can calculate your concentrations also, but generally for a simple analysis you kind of just go with the flow and add the solvent if it is too concentrated or add more sample if it is too dilute, okay? So you have to get it to the right concentration though in order to get to the right scale for the lambda max. Now, in UV-Vis, the area under the graph is meaningful, okay? And so for that, you really need to have a specific concentration and you need to use Beer's law in order to calculate that, okay? And so that's something that can be done and is usually done when you're reporting your data for publication, then you have to do that kind of work also, okay? The good thing about UV-Vis, you can definitely recover your sample. Just evaporate the solvent and you have your sample. Okay, so let's talk a little bit about analyzing the spectrum. What are you looking for? What are you doing, okay, in the UV-Vis? Okay, you understood the theory part of it, okay, that there are electron transitions happening. So first of all, you're just getting a graph really quick, okay? You put your sample, you hit run, and this is the graph you get, okay? So this is for isoprene, 2 double bonds, and this is all in the UV region. The UV region is running from 200 to 400, okay? So which means it's not visible. Remember, only colored compounds will show in the visible region, right? Right? You got that? Okay. So here this is the UV spectrum only. It's not going to show up in the visible because not colored compound. So this is the spectrum you're getting. Okay, so what we're saying here is that the lambda max is 222, and that's good. Okay, that's it. That's the data. You can't predict this, by the way. In some cases you can, and there are rules. Okay, you can follow those rules. Those are called Hoffman rules. We follow those, and you can actually calculate you know, a little bit about if you add a methyl group or if you add another double bond, what's going to happen to your lambda max. You can calculate that. We're not going to do that, but I'm just telling you, okay, that you can if you wanted to. Now, the area under the graph, as I said, is an important thing, okay, for most of the people working in UV spectroscopy. And that's because this tells you how many electron transitions are possible here. So you see that there is a huge curve here, right? There's a lot of space underneath that graph. Now let's just consider that maybe you had another small peak over here. Let's just say that. What does this tell you? Now, this is also a lambda max, but what this is telling you is that these electron transitions are not that possible, conducive, you know, they're not that much of electron transitions here. So you have two electron transitions. These ones, yeah, very happy. These ones, not so much, okay? So you can tell you know, which transitions are going to be possible. Now, photochemists generally who work with this a lot, they can actually figure this out. Okay, now we are not going to, so don't be scared. But if you're a photochemist, you can actually look at these graphs and you can figure out, oh, okay, this is the, you know, this kind of a transition going on, this pi to this pi or sigma to pi, whatever kind of transitions. You can look at all of that, okay? So here I've given you the Beer's law also, which is used to calculate the area under the graph, which is called the extinction coefficient, okay, or molar absorptivity, which is epsilon. So A is equal to epsilon CL. A is the absorbance, that is equal to the area under the graph. C, which is the concentration of the sample, that's when you have to calculate the concentration. So you have to make a specific molarity of your sample. And then L is the length of the path, okay? And this is an important thing because when you have, you know, a cuvette, for example, all right, something like this, that cuvette, that length of the light that's passing through is an important thing. Okay, so this is 1 centimeter usually. That's how cuvettes are made. That's why I showed you the sample holder, you know, that it's a cuvette. What I didn't mention is it's 1 centimeter. It's a very specific length. Okay, so even in the UV-Vis, the holder, the actual sample holder is, you know, is made specifically to accommodate this cuvette. The length of the light going through is really important. And I want you to imagine one thing about, you know, what I'm talking about here. If you go to the beach and if you look out in the ocean, you're going to see different shades of blue. Okay, and that's because there are different number of ions in there, and there's also different depth. Okay, even if the ions were the same, the different depth, okay, of the ocean will give you different colors, which means how much light is passing through, okay, in that distance will change the color, okay, of something. And that's why it's really important for us to keep the 1 centimeter. If this is one thing you want to completely forget, you're most welcome to, okay, because we're not calculating anything in Beer's law, but I want you to understand that how much light is absorbed changes with how much distance it is traveling within the solvent, okay, or within the solution. So a beach is a good example, okay? So I hope you understand what I'm talking about. So that's why we use the Beer's law here to figure out the area under the graph, okay? Because this tells us the transitions that are happening. The concentration that I was explaining to you has to do with also the energy, okay? So you want to keep that distance constant. The L, sorry, not the concentration, the L. The concentration also has to be kept, you know, specific, because if you change the concentration, you change how much energy is being given, okay? So, I mean, it's a very specific kind of a technique. Okay, so what are we doing here? Okay, what we're doing here is we're looking for conjugation. Okay, so here are some examples of different kinds of compounds giving you different absorption. So that's all I have given you here. Is if you have an isolated double bond, look at them, they're all coming at around 180 or 170. This is an isolated double bond, right? So one here separated by an sp3 carbon. They don't really absorb that much, which means that they are coming at very high energy. Low wavelength means high energy. When you start having conjugated dienes, when you start having more conjugation, then look at that, the absorption increases, okay, which means that the HOMO and the LUMO are coming closer, the transitions are becoming easier, so that energy, okay, that the molecule absorbs is also getting lower, okay, in there, so higher wavelength. Once you have even more double bonds in there, then it gets even higher and higher. Okay, so that's kind of how it goes for any kind of conjugated system, and this is definitely not a triene, so I'm going to fix that, but that's just a polyene. So in any case, okay, the more conjugation you have, the more absorption you will have, which means the higher the wavelength. Okay, so here are some absorptions for dyes, and dyes we know are all colored, and all of these are absorbing in the visible region. Okay, so you can see all the conjugation that is in all these compounds, how many double bonds, okay, they have. So the more double bonds you have, the more conjugation you have. One thing I can explain to you a little bit about, the visible spectrum is that, here. This is 400, this is 800, 200. So this is the UV region, this is the visible region, okay? So 400 is high energy, this is the violet region. The 800, this is the red region. After that, it's IR, by the way, okay? So here, generally, we say if something is more red shifted, means that something is low energy. Violet would mean it's a blue shift, and that is higher energy. Okay, so higher wavelength means that you have low energy. All right, so think in those terms if you want to, and again, more conjugation will lead to more of a red shift. Okay, not all the time, not all the cases, but because there's so many other things also involved here. Okay, but that's kind of a general thinking, and that's how I would like you to answer some of the questions that we do. Okay, also. So here I just wanted to show you the absorption for chlorophyll, okay? Chlorophyll is, of course, a beautiful compound that we have in leaves, and we know also how leaves change colors in fall, for example. So you see all sorts of beautiful colors, going on in there, red, green, orange, yellow, all sorts of colors. So they all come from this beautiful molecule called chlorophyll, which is so conjugated, and you have different kinds of chlorophylls, and then when the chlorophyll will start degrading in fall, because when the cold weather hits and the chlorophyll starts degrading, then you start getting those beautiful colors, okay? And they are still conjugated systems, but a little bit different. Generally, chlorophyll is going to be blue-green, okay? Generally, that's how it's supposed to be. But look at the spectra of it, and what I wanted to show you here, again, nothing for you to remember here if you don't want to, is how big these lambda maxes are, and also the fact that you have such a huge peak on the right side, on the red side also, okay, over here, which tells you a lot of electron transitions here, a lot of electron transitions here also, okay, going on. Just to show you, that's all, nothing there. Okay, now for each set of these compounds, we have a worked example. Let's look at that. So increasing wavelength. So you need to know what kind of questions I'll be asking you, right? That's the main thing. So, okay, I have two problems here. One, so arrange them in order of increasing wavelength. Increasing wavelength means the higher nanometers. Higher nanometers means that something that is lower in energy. Okay, so how does this work? You look at conjugation. So for example, number 2 I can see is conjugated, is going to have the lowest energy. This is single double bond, so this is going to have the highest energy, okay, for it. So that's how it should be. So 2 is going to be higher in wavelength, low energy, remember that, okay? So this is higher in wavelength, and 1 is going to be the shortest wavelength, okay? So keep those things in mind, okay? Again, let me write them for you, okay? Higher nanometer means low energy. Okay, that's what it really means. So increasing wavelength is what I asked for. So this is going to be the most increasing wavelength because this is more conjugated. Okay, that's how it's working. Okay, here's the next one, and I'm sure you can figure this out. I can give you a minute, but then I'd be wasting a lot of video. You can pause if you want, and you can, try to solve this yourself. But looking at this, I can see this is, the first one is more conjugated, and this one is the least conjugated, right? So most conjugated mean that you would have a higher nanometer for that. Okay, so hopefully that's the answer. So 1 is going to be the largest wavelength, and 2 will be then the lowest. And that's the kind of questions I can give you here. I'm not going to ask you to draw any molecular orbitals in here. I can only ask you to figure out, what's the higher wavelength. So that's only conjugation. That's all. I like UV-Vis because I work with UV-Vis. And I really enjoyed working with colored compounds, so that was kind of fun for me. Anyhow, so just, make sure that you understand conjugation, which you, I think, can, and then which one will absorb more in the red or the violet region, okay, or in the UV region also. That's it.